Find somewhere comfortable tonight, somewhere the day can't quite reach you. You don't need to follow any of this closely. You don't need to hold on to the details, or remember the names, or keep track of where we are. The words will arrive in their own time, and you can let them pass through you like light through water, changing the color of things slightly, without you having to do anything at all. We're going to spend some time tonight with one of the deepest questions human beings have ever asked. Not a question about history or about each other, but about the universe itself, about what it is actually made of and how much of that we cannot see and may never touch. It is a question that has been gathering for about 100 years now, quietly at the edges of telescopes and in the margins of notebooks, and it has not yet been answered. Perhaps that is part of why it feels so restful to think about. Only the question, growing gradually more beautiful the longer you sit with it. So settle in. Let your weight fall where it wants to fall. The night is long, and we are in no hurry, and the universe has been keeping its secrets for nearly 14 billion years. A little longer won't trouble it at all. Begin, if you will, with what we thought we knew. For most of human history, the night sky was simply there, a fixed and permanent ceiling scattered with points of light that our ancestors named and navigated by and told stories about. The stars were beautiful, and they were distant, and for a very long time, that was more or less the full extent of our relationship with them. They shone. We looked up. The arrangement seemed complete. Even as science developed its tools. The telescope, the spectroscope, the photographic plate, our picture of the universe remained, in its broad outlines, a picture of things we could observe. Matter was what you could see, or at least what you could in principle detect. The universe was its light. The first quiet disturbance to that picture came from a Dutch astronomer named Jacobus Kapteyn, working in the early years of the 20th century. Kapteyn was a careful, methodical man, the kind of scientist who spent decades counting stars, cataloguing their positions and their motions, building a statistical portrait of the Milky Way from the ground up. He was one of the first people to attempt a systematic map of our galaxy, and by 1922, he had accumulated enough data to make an observation that was, at the time, easy to overlook. He noticed that the mass of the Milky Way, the total gravitational pull implied by the way stars moved within the galactic plane, seemed to be greater than the stars themselves could account for. The stars were moving as though something else was there with them, something that didn't shine. He wrote about it with characteristic restraint, suggesting that there might be dark matter. He used those words, in English, present in the galactic plane. It was a tentative remark, almost a footnote, and the scientific community received it with the polite attention one gives to a footnote, then moved on. But the question had been asked. It was in the literature now, waiting. The person who would ask it more loudly and more insistently and with considerably less politeness was Fritz Zwicky. Zwicky was Swiss by birth, American by adoption, and difficult by disposition. He worked at the California Institute of Technology and spent many of his most productive years at the Palomar Observatory in the mountains east of Los Angeles, a place of cold nights and extraordinary seeing, where the darkness comes down so completely that the Milky Way casts a shadow. He was, by most accounts, a brilliant and combative man who referred to his colleagues as spherical bastards, meaning, he explained, that they were bastards any way you looked at them. He was also, as it turned out, right about something enormous. In 1933, Zwicky turned his attention to the Coma Cluster, a vast collection of galaxies roughly 320 million light-years from Earth. The Coma Cluster contains hundreds of galaxies, all of them gravitationally bound together, or so it appeared. Zwicky measured the velocities of those galaxies, and what he found troubled him deeply. To understand why, you need to think about what holds a gravitational system together, whether it is a planet orbiting a star orbiting a galaxy, or a galaxy orbiting within a cluster. The same principle applies. The speed at which an object moves must be balanced against the gravitational pull of the mass at the center. If the object is moving too fast for the gravity available, it will fly away like a stone released from a sling. If it is moving too slowly, it will fall inward. Stable orbits require a precise match between velocity and gravity. Zwicky measured the velocities of the galaxies in the Coma cluster, and they were far too high. Not a little too high. Vastly too high. The galaxies were moving at speeds that should have sent them flying apart millions of years ago. The cluster should not exist. And yet, there it was, hanging together in the night sky, cohesive and apparently stable. Zwicky calculated how much mass would be needed to hold the cluster together at those velocities. The answer was startling, roughly 400 times more mass than all the visible galaxies in the cluster could provide. 400 times. The stars and gas he could see accounted for perhaps 0.25% of what gravity was telling him must be there. He named the missing substance Dunkel Materie, dark matter in German, and he published his finding, and the scientific community did what it often does with ideas that are too large and too strange to absorb immediately. Part of the problem was Zwicky himself. His personality made it easy to dismiss his results as the overreach of a difficult man. Part of the problem was the era. The tools for confirming or refuting his calculation were limited, and other explanations, measurement error, unusual gas distributions, seemed at least plausible. And part of the problem was simply that the claim was so extreme, 400 times the visible mass, hidden somewhere, doing nothing but pulling. The idea sat at the edge of credibility and stayed there for decades. But the mathematics did not go away, and the Coma cluster did not fly apart. Zwicky spent the rest of his career at Palomar, studying supernovae and neutron stars and galaxy clusters, making contributions that would not be fully appreciated until long after he was gone. He died in 1974, just as the evidence for dark matter was beginning elsewhere to become undeniable. He was difficult, and he was right, and the universe did not particularly care which of those facts people found more convenient to hold. The gravity was pulling harder than anything anyone could see. That was the fact, and eventually the facts accumulate to a weight that no amount of skepticism can resist. If Fritz Zwicky fired the first shot, it echoed mostly in silence. The evidence that finally changed the conversation came not from a cluster of galaxies hundreds of millions of light years away, but from something closer and more patient. The slow, steady rotation of individual spiral galaxies measured one Kertel spectrum at a time. And the person who did that measuring over years of quiet, meticulous work was Vera Rubin. Rubin grew up in Washington, D.C., the kind of child who moved her bed to watch the stars wheel overhead through her bedroom window. She earned her doctorate in 1954, at a time when women in professional astronomy were tolerated rather than welcomed, a time when she was told, as a young student, that the Princeton graduate program in astronomy did not accept women, and responded by going to Cornell instead. She was sharp and persistent and deeply serious about the work, and she had a gift for choosing problems that sat just at the edge of what was technically possible. By the late 1960s and into the 1970s, working with the instrument builder Kent Ford at the Carnegie Institution in Washington, Rubin had turned her attention to the rotation curves of spiral galaxies. What she was doing, in essence, was measuring how fast different parts of a galaxy were orbiting around the galactic center, and comparing that to what physics predicted she should find. The prediction was clear, and it came from the same source as all orbital mechanics, Newton's law of gravitation. The principle is simple at its core. Gravity weakens with distance. The further you are from a massive object, the weaker its pull on you, and weaker gravity means slower orbits. Think of our own solar system. Mercury, the innermost planet, races around the Sun at about 47 kilometers per second. Earth travels at roughly 30 kilometers per second. Neptune, out near the cold edge of the solar system, crawls along at just over 5 kilometers per second. The pattern is unmistakable. The further from the Sun, the slower the orbit. This is not a coincidence or a preference. It is a direct consequence of how gravity works. The reason follows from a beautiful piece of reasoning. For an object in a stable circular orbit, the gravitational pull inward must exactly equal what physicists call the centripetal force needed to keep it moving in a circle rather than flying off in a straight line. Gravity falls off with the square of the distance. Double your distance from the center of mass, and gravity drops to a quarter of its former strength. To stay in orbit at that weaker gravity, you need to move more slowly. The mathematics works out precisely. Orbital speed should decrease in proportion to the square root of the distance from the center. In the solar system, this relationship, known as Keplerian rotation, after Johannes Kepler, who described it in the early 17th century, fits the data with extraordinary precision. Now apply the same logic to a spiral galaxy. A spiral galaxy, like our own Milky Way or like Andromeda, has most of its visible mass concentrated toward the center. A dense bulge of stars surrounded by a flatter disk that thins out toward the edges. If the mass is concentrated in the middle, then stars near the center should orbit quickly, and stars out toward the rim should orbit more slowly, just as Neptune is slower than Mercury. The rotation curve, a graph of orbital speed against distance from the center, should rise steeply near the core, peak somewhere in the inner disk, and then fall away smoothly as you move outward. That was the prediction. That was what every physicist expected to see. Rubin and Ford pointed their spectrograph at the Andromeda galaxy and began measuring. A spectrograph works by splitting the light from a source into its component wavelengths, its spectrum, and looking for the characteristic fingerprints of known elements. When a source of light is moving toward you, those fingerprints shift slightly toward the blue end of the spectrum. When it is moving away, they shift toward the red. By measuring how much the fingerprints shift at different points across the face of a galaxy, you can calculate the orbital velocity at each point with remarkable precision. It is the same principle as the change in pitch of a passing ambulance siren applied to light instead of sound. They measured, and then they measured again, because what they were seeing was not what the equations said should be there. The stars in the outer regions of Andromeda were not slowing down. They were moving at roughly the same speed as the stars much closer to the center. The rotation curve was flat, not the gracefully declining arc that Newtonian physics demanded, but a horizontal line that stubbornly refused to drop. Rubin extended the work to other galaxies, then to dozens of galaxies. The result was the same. Again and again, flat rotation curves. Stars at the outermost edges of spiral galaxies orbiting just as fast as stars deep in the inner disk. In some galaxies, the speed even seemed to increase slightly with distance before leveling off. This was, to put it plainly, impossible. If the only mass in the galaxy was the mass you could see. Think about what a flat rotation curve actually implies. If the orbital speed stays the same as you move outward, if it does not fall off as distance increases, then the gravitational pull at each distance must also stay the same, or close to it. But gravity from a concentrated central mass weakens with distance. The only way to maintain a constant gravitational pull as you move outward is if there is more mass being added as you go further out. Mass that keeps accumulating even beyond the visible edge of the galaxy. The conclusion was inescapable, and Rubin stated it with characteristic directness. The visible galaxy, all the stars and gas and dust you can see in the disk, must be embedded within an enormous invisible halo of mass that extends far beyond the luminous boundary. a halo of dark matter, perhaps 10 times more massive than all the visible stars combined, spherical in shape, reaching out into the darkness well beyond where the last star shines. The initial response from the astronomical community was skeptical. Some suggested the measurements were in error. Others proposed that the discrepancy might be explained by unseen gas or by errors in estimating how much mass the visible stars actually represented. The idea that most of every galaxy was invisible, that the brilliant spiral structures we had spent centuries admiring were, in some sense, a minor decoration on a vast dark structure we could not see, was not easy to accept. But Rubin had data from more than 60 spiral galaxies, and the pattern held across all of them. The skepticism gradually, grudgingly, gave way. By the early 1980s, the flat rotation curve had become one of the most robustly established observations in astrophysics. It was the simplest explanation for something that had been measured carefully, many times over. Rubin herself was thoughtful about what the work meant. She did not claim more than the data supported. She noted that the ratio of dark matter to visible matter in a typical spiral galaxy was roughly 10:1, meaning that for every kilogram of star and gas and dust you could see, there were about 10 kilograms of something else, something that produced no light, left no spectral fingerprint, and made its presence known only through the pull it exerted on everything around it. She also said something else, something that has stayed with anyone who has heard it. She said that the ratio of dark to visible matter, 10:1, was probably a reasonable estimate for the ratio of our ignorance to our knowledge. We are out of kindergarten, she said, but only in about 3rd grade. It is a generous way to describe the situation, and a humbling one. The woman who proved that most of the universe is invisible was also the first to say, quietly and without drama, that she had no idea what it was. There is another way to find what cannot be seen, and it is perhaps the most beautiful method in all of science. It requires no spectrograph, no measurement of velocity, no inference from motion. It requires only the understanding that gravity does not merely pull on matter. It shapes the space through which everything, including light, must travel. This idea came from Albert Einstein, and it was one of the most radical reconceptions of physical reality ever proposed. Newton had described gravity as a force, a pull between masses, acting across empty space instantaneously with a strength that fell off with the square of the distance between them. The description was extraordinarily accurate. It predicted the orbits of planets, the trajectories of cannonballs, the return of comets. For more than 2 centuries, it was the framework within which all of physics operated. But Newton himself was uncomfortable with one aspect of his own theory. He could not explain how gravity acted across empty space, how the sun could reach out across 150 million kilometers of nothing and pull the Earth toward it. He called it action at a distance, and he admitted, famously, that he had no hypothesis about how it worked. Einstein's answer, published in his General Theory of Relativity in 1915, was to reframe the question entirely. Gravity, he proposed, is not a force in the traditional sense at all. It is a consequence of the geometry of space and time. Mass. Any mass. The Earth orbits the Sun, not because the Sun is pulling it with an invisible rope, but because the Sun has bent the space around it into a kind of bowl, and the Earth is following the straightest possible path through that curved geometry. From the Earth's perspective, it is moving in a straight line. From the outside, that straight line through curved space traces out an ellipse. Now here is the crucial step. If space-time itself is curved by mass, then everything that travels through space-time must follow that curvature, including light. Light always travels in a straight line, but in curved space, a straight line is not what you might intuitively expect. Near a massive object, the straightest possible path through space bends toward the mass. This means that light from a distant object passing close to a massive foreground object on its way to your eye will be deflected. The path of the light will curve around the mass the way a stream of water curves around a stone. And this has a remarkable observational consequence. The distant object will appear to be in a slightly different position than it actually occupies because the light reaching you has been bent on its journey. Einstein predicted this effect, and it was confirmed with famous drama during the solar eclipse of 1919 when the British astronomer Arthur Eddington measured the positions of stars near the edge of the sun, stars that should have been invisible but could be seen during totality, and found that their apparent positions were shifted by exactly the amount Einstein had calculated. The news spread around the world. General relativity was confirmed. Einstein became, overnight, the most famous scientist alive. But the applications of gravitational lensing, as the bending of light by mass came to be called, extended far beyond confirming a theory. They offered something more practically useful, a way to weigh objects you cannot otherwise measure. Here is why. The amount by which a massive object bends the light passing near it depends directly on how much mass that object contains. More mass means more curvature, means more bending. If you can measure the degree of bending by observing how much a background object's image is distorted or displaced, you can calculate the mass of the foreground object that caused it, regardless of whether that mass emits any light at all. In the case of a galaxy or a galaxy cluster acting as a gravitational lens, the distortions can be dramatic. A perfectly aligned foreground mass and background galaxy will produce what is called an Einstein ring, a complete circle of light around the foreground object, formed because the background galaxy's light has been bent equally in all directions. Partial alignments produce arcs, elongated and curved like fragments of those rings. Multiple images of the same background object can appear, separated and sometimes mirrored, each one a different path the light took around the foreground mass. By mapping these arcs and rings, by measuring their geometry and brightness carefully, astronomers can reconstruct the distribution of mass in the foreground cluster. The mass map they produce includes everything: visible stars, hot gas, and any invisible matter that is contributing to the gravitational deflection. This technique became one of the most powerful tools in the dark matter toolkit, and nowhere was it applied to more spectacular effect than in the observation of a structure known as the bullet cluster. The bullet cluster, its formal designation is 1E065758, is actually two galaxy clusters that collided with each other roughly 150 million years ago at a speed of around 3,500 kilometers per second. At that velocity, the collision was one of the most energetic events in the universe since the Big Bang itself. By the time astronomers turned their instruments toward it, the collision was over, and the two clusters were moving apart from each other, leaving behind a mess that turned out to be extraordinarily informative. When two galaxy clusters pass through each other, different components of each cluster behave differently. The individual galaxies, which are, despite appearances, mostly empty space, pass through each other like two swarms of bees, largely without colliding. But the hot gas that fills the space between galaxies, and this gas is actually the majority of the ordinary visible matter in a cluster, is a fluid, and fluids collide. The hot gas from both clusters slammed into each other, was compressed and heated, and was slowed dramatically. It piled up in the middle of the collision zone, glowing brilliantly in X-ray light, forming a distinctive shape that gave the bullet cluster its name. One cluster had passed through the other like a bullet through a target, leaving a bowshock of hot gas in its wake. NASA's Chandra X-ray Observatory mapped this hot gas with exquisite precision. The gas was clearly concentrated in the middle of the collision zone, between the two separating clusters, glowing in X-rays at temperatures of tens of millions of degrees. But then, astronomers applied gravitational lensing analysis to the same region, using the distortions of background galaxies to map the total mass distribution. including any invisible mass, across the entire system. The lensing map did not match the X-ray map. Not at all. The lensing map showed two distinct concentrations of mass, one associated with each of the two departing clusters, sitting well ahead of the hot gas in the direction each cluster was moving. The total gravitational mass had not been slowed by the collision. It had passed straight through, unimpeded. This is exactly what you would expect if most of the mass in each cluster was made of dark matter. Dark matter, by its nature, does not interact with ordinary matter through the electromagnetic force. It has no charge, it does not feel the pressure of gas, it does not slow down in a collision, it simply passes through. The dark matter halos of both clusters had moved through each other like ghosts, continuing on their trajectories while the hot gas, the visible, ordinary matter, was left behind in the middle, slowed and compressed by the collision. The result was a direct spatial separation between the ordinary matter and the dark matter. A map. You could look at the two images side by side, the X-ray glow of the hot gas piled in the center and the gravitational lensing contours of the total mass displaced ahead of it on either side, and see, without ambiguity, that the mass of these clusters was not where the visible matter was. It was one of the most direct pieces of evidence for dark matter ever assembled, not an inference from velocities, not a theoretical argument, but a picture. Here is where the ordinary matter ended up, and here, separately, is where most of the mass actually is. The bullet cluster did not prove what dark matter is, but it made it very difficult to argue that dark matter is not there at all. To understand dark matter fully, you have to travel further back than galaxies, further back than stars. You have to go back to a time before any of those things existed, back to the first moments of the universe, when everything that would ever be was compressed into something unimaginably hot and dense, and the question of what form the universe would eventually take was still, in a sense, open. The Big Bang happened approximately 13.8 billion years ago. In the first fractions of a second, the universe was a seething plasma of energy and elementary particles, protons, neutrons, electrons, photons, neutrinos, and, we now believe, dark matter particles, all at temperatures so extreme that no atom could form. The energy density was so high that matter and energy were essentially interchangeable, particles being created and annihilated in constant churning exchange. As the universe expanded, it cooled. This is one of the most important facts in cosmology. Expansion and cooling are linked. The universe is like a gas expanding into a larger volume. As it spreads out, its temperature drops. And as the temperature dropped, the universe passed through a series of thresholds, each one marking a moment when something new became possible. For the first 380,000 years, the universe was still too hot for electrons to settle into stable orbits around atomic nuclei. Every time an electron approached a proton, a photon with enough energy came along and knocked it free again. The universe was opaque, a fog of charged particles through which light could not travel freely, because light is constantly scattered by charged particles, the way sunlight is scattered by fog. Then, at around 380,000 years after the Big Bang, the universe cooled to a temperature of roughly 3,000 degrees, about half the surface temperature of our Sun today. At that threshold, electrons could finally settle into stable orbits. Hydrogen atoms formed for the first time in their billions upon billions upon billions upon billions. And the universe, almost instantaneously by cosmic standards, became transparent. The photons that had been trapped in the plasma, scattered endlessly, unable to travel freely, were suddenly released. They streamed outward in all directions, and they have been traveling ever since. Today, 13.5 billion years later, those same photons are still out there, filling all of space, cooled by the expansion of the universe to a temperature of just under 3 degrees above absolute zero. They form a faint background glow of microwave radiation, the cosmic microwave background, a snapshot of the universe at the moment it first became transparent. This background glow is one of the most important objects in science. When NASA's WMAP satellite and later the European Space Agency's Planck satellite mapped it with great precision, they found that it was not perfectly uniform. It was almost perfectly uniform. The temperature was the same in all directions to about 1 part in 100,000, but embedded in that near uniformity were tiny fluctuations, patches slightly warmer and slightly cooler than average. Those tiny fluctuations were not noise, they were signal. They were the imprint of density variations in the early universe, regions where matter was slightly more concentrated and regions where it was slightly less so. And the pattern of those fluctuations, their size, their spacing, their relative amplitudes, contains an enormous amount of information about what the early universe was made of. When cosmologists analyze the pattern of fluctuations in the cosmic microwave background, one of the things they can extract is the ratio of ordinary matter to dark matter. The fluctuations act like the ringing of a bell. Different compositions of matter produce different harmonics, different patterns of peaks and troughs in the temperature map. The observed pattern fits one particular composition with extraordinary precision, roughly 5 times as much dark matter as ordinary matter present in the early universe. If you remove dark matter from the equations and try to fit the fluctuation pattern with ordinary matter alone, the fit breaks down. The peaks come out wrong. The pattern does not match. The universe, as we observe it, from this faint microwave glow, is only consistent with the presence of a large quantity of something that does not interact with light. But the cosmic microwave background tells us more than just the ratio. It also tells us something about the nature of dark matter, specifically about how it behaved in those early moments before atoms had formed. Here is the key distinction. Ordinary matter, protons, electrons, the stuff of atoms, interact strongly with photons through the electromagnetic force. In the hot, dense early universe, the pressure of radiation was enormous, and it pushed ordinary matter around. Wherever ordinary matter tried to clump together under its own gravity, the pressure of the surrounding radiation would push back, preventing the clump from forming. This created a kind of oscillation. Gravity pulled matter inward, radiation pressure pushed it outward, and the result was sound waves rippling through the early universe, waves of compression and rarefaction in the matter, radiation plasma. Dark matter experienced gravity, but it did not interact with photons. It felt no radiation pressure. It was immune to the push of light. This meant that from very early on, long before the universe became transparent, long before ordinary matter could begin to clump, dark matter was already quietly gathering itself together. Wherever there was a slight overdensity of dark matter, its gravity attracted more dark matter, and the overdensity grew. Slowly, patiently, over millions of years, dark matter assembled itself into structures, filaments and sheets and nodes, a vast three-dimensional web of invisible mass. By the time the universe became transparent and ordinary matter was finally free to move, the dark matter web was already there, waiting. The ordinary matter fell into the gravitational wells that dark matter had prepared. Gas collected along the dark matter filaments, pooled at the nodes where filaments intersected, and eventually, over hundreds of millions of years, collapsed into the first stars and the first galaxies. The large-scale structure of the universe, that cosmic web of galaxy filaments and vast empty voids that astronomers have mapped over the past few decades, is, in this sense, a tracing of the underlying dark matter structure. The galaxies and galaxy clusters we see are not random. They sit where the dark matter told them to sit, having followed gravity's patient invitation inward over billions of years. This has been confirmed by computer simulations of extraordinary sophistication. When you run a simulation of the universe's evolution that includes dark matter in the right proportion, the result, after billions of simulated years, produces a cosmic web that matches, with remarkable fidelity, what we actually observe: the same filaments, the same voids, the same clustering of galaxies at the intersections of the web. When you run the same simulation without dark matter, using only ordinary matter, the result is a universe that looks nothing like ours. The structures are wrong. The galaxies cluster in the wrong places. The voids are the wrong size. Dark matter is not merely present in our universe. In a very real sense, it is the reason our universe looks the way it does. The galaxies, the stars, the planets, the particular arrangement of everything we have ever seen, all of it grew in the shape that dark matter carved out, in the patient dark, long before the first light was born. So we know dark matter is there. We know it outweighs visible matter by roughly 5-to-1 across the universe as a whole, and by closer to 10-to-1 within individual galaxies. We know it shaped the large-scale structure of everything. We know it holds galaxies together and keeps clusters from flying apart. What we do not know, and this is one of the deepest open questions in all of physics, is what it actually is. What is the stuff? What are its properties? If you could hold a piece of it, what would you be holding? To approach this question, it helps to understand the 4 fundamental forces through which matter interacts. Everything in the physical world is governed by 4 basic interactions. The first is gravity, which acts on anything with mass or energy, and which operates across all distances, though it grows weaker with distance. The second is the electromagnetic force, which governs the interactions of charged particles. It is the force responsible for light, for chemical bonds, for the behavior of electrons, for essentially everything you experience in daily life. The third is the strong nuclear force, which holds the nuclei of atoms together, binding protons and neutrons against the electromagnetic repulsion that would otherwise drive them apart. And the fourth is the weak nuclear force, which governs certain kinds of radioactive decay and plays a role in processes like the nuclear fusion that powers the sun. Ordinary matter, atoms, molecules, stars, planets, you, interacts through all 4 of these forces, though in different contexts and to different degrees. Dark matter, whatever it is, clearly does not interact via the electromagnetic force. If it did, it would absorb or emit light, and we would have detected it long ago. It also appears not to interact via the strong nuclear force, which would make it sticky and clumping in ways we do not observe. That leaves gravity, which everything has, and possibly the weak nuclear force. The leading candidate for dark matter, the particle that has attracted the most theoretical attention and the most experimental effort, is something called a weakly interacting massive particle, known by the acronym WIMP. The name describes the particle's properties precisely. It is massive, meaning it has significant mass, perhaps somewhere in the range of 10 to 1,000 times the mass of a proton, and it interacts weakly, meaning it responds to the weak nuclear force and to gravity, but not to the strong or electromagnetic forces. A particle with those properties would be, for practical purposes, invisible. It would pass through ordinary matter almost without interaction. Trillions of WIMPs could be streaming through your body at this moment, and the chance of any single one of them nudging an atom in your body is so small as to be effectively zero. They would pass through walls, through the earth, through stars, interacting only very occasionally, when a WIMP happened to pass close enough to an atomic nucleus for the weak force to act. The theoretical case for WIMPs rests partly on what physicists call the WIMP miracle, a phrase that captures a genuinely remarkable numerical coincidence. In the very early universe, when temperatures were high enough, WIMPs would have been produced and destroyed continuously like all other particles in a constant churning of creation and annihilation. As the universe expanded and cooled, the temperature eventually dropped below the threshold needed to create new WIMPs. The energy was no longer sufficient. At that point, WIMP creation stopped, and the remaining WIMPs began to annihilate each other in pairs. As the universe continued to expand, WIMPs became rarer, and the rate at which they could find each other and annihilate slowed. Eventually, the universe had expanded enough that WIMPs were too spread out to find each other at all, and the annihilation effectively stopped. A relic population of WIMPs was frozen in, the survivors of that early era drifting through the universe ever since. The remarkable thing is that when you calculate how many WIMPs would survive this process using the mass range and interaction strength suggested by particle physics for other reasons entirely, the answer comes out to roughly the right number to explain the dark matter we observe. A particle of about 100 times the mass of a proton interacting through the weak force would naturally produce a relic abundance that matches what cosmology tells us must be there. This is the WIMP miracle, the coincidence that a particle motivated by completely separate considerations in particle physics, by the mathematics of the weak nuclear force, by the symmetries of the standard model of particle physics, would also happen to be produced in exactly the right quantity to be the dark matter. It is the kind of coincidence that physicists take seriously, because in physics, when numbers that have no obvious reason to be the same turn out to be the same, it often means something. But WIMPs are not the only candidate. There is another, in some ways even more intriguing, the axion. Axions were not originally proposed as a dark matter candidate. They were proposed in the late 1970s by the physicists Roberto Pecchesi and Helen Quinn to solve a completely separate puzzle in particle physics. A puzzle about why the strong nuclear force appears to be perfectly symmetric between matter and antimatter, when the equations describing it suggest it need not be. The axion was the mathematical solution to that puzzle, a new particle whose existence would explain the symmetry. Only later did physicists realize that axions, if they exist, would also have been produced abundantly in the early universe, and that they could, under the right circumstances, account for the dark matter. Axions are very different from WIMPs. They are extraordinarily light, perhaps 10 trillion times lighter than an electron, which is itself nearly 2,000 times lighter than a proton. They interact so weakly with ordinary matter that they make WIMPs look sociable by comparison. Under normal circumstances, an axion would pass through everything without leaving any trace. But there is one interaction that axions are predicted to have, and it offers a detection route. In the presence of a very strong magnetic field, an axion can spontaneously convert into a photon, a particle of light. The photon produced has a specific energy, determined by the axion's mass. If you build a device with a strong magnetic field and a sensitive detector tuned to the right frequency, you might, in principle, catch an axion in the act of becoming light. The detection strategies for WIMPs and axions are therefore completely different, which matters because we do not know which one, if either, is the answer. The universe might contain WIMPs, or axions, or both, or something else entirely that theorists have not yet imagined. The question of what dark matter is made of is genuinely open, and the search for an answer is one of the most active frontiers in experimental physics. What we can say is this: whatever dark matter is, it is something new. Something outside the standard model of particle physics, which describes every particle we have ever directly detected. It is a gap in our most comprehensive theory of matter, a gap whose shape we know very well, whose gravitational footprint we have mapped across the entire observable universe, but whose contents remain unknown. That is a strange and somewhat wonderful position to be in. We have weighed something we have never seen. We have traced its distribution across billions of light years. We have constrained its properties with great precision, and we still do not know what it is. The search for dark matter is being conducted in places as different from each other as it is possible to imagine. A gold mine nearly a mile beneath the grasslands of South Dakota, a tunnel beneath the Gran Sasso Mountain in central Italy, and a laboratory at the University of Washington where physicists listen for the faint ring of a microwave cavity. Each of these experiments is designed around a different strategy, and each is pushing the boundaries of what can be measured. The reason these experiments go underground is straightforward and worth understanding fully. The Earth is constantly being bombarded by cosmic rays, high-energy particles arriving from space, mostly protons and atomic nuclei accelerated to enormous velocities by violent events like supernova explosions. When these particles hit the upper atmosphere, they create cascades of secondary particles that rain down through the air and through everything below it. At the surface of the Earth, you are being struck by hundreds of these secondary particles every second, passing through your body without you noticing. For a dark matter detector, these cosmic ray particles are an overwhelming source of noise. If you are trying to detect the faint recoil of a single atomic nucleus nudged by a passing dark matter particle, an event so rare and so gentle that it might happen only a handful of times per year in a ton of detector material, you cannot afford to have hundreds of cosmic ray particles per second crashing through your apparatus and mimicking the signal you are looking for. The solution is depth. Rock is an excellent shield against cosmic rays. As cosmic ray particles travel through rock, they lose energy and are absorbed. At a depth of roughly a mile underground, the rate of cosmic ray particles reaching your detector drops by a factor of millions compared to the surface. The rock filters out the noise, leaving a quiet environment in which the rarest of events might be noticed. The Luix Zeppelin detector, the name is built from the initials of its predecessors, the Large Underground Xenon Experiment and the Zeppelin experiments, sits at the Sanford Underground Research Facility in Lead, South Dakota, in tunnels carved out during the gold mining era. The detector itself is a cylinder containing about 10 tons of liquid xenon, cooled to temperatures around -100 degrees Celsius, where xenon is a dense, clear liquid. Xenon is chosen for a specific reason. If a dark matter particle, a WIMP, were to pass through the detector and interact with an atomic nucleus, the nucleus would recoil like a billiard ball struck by another. That recoil would produce two signals simultaneously, a flash of ultraviolet light as the recoiling nucleus excited nearby xenon atoms, and a small cloud of electrons liberated from those atoms by the energy of the collision. The electrons drift upward through the liquid xenon under the influence of an electric field and produce a second flash of light when they reach the top of the detector. The ratio of the two flashes and their timing allows physicists to distinguish a genuine nuclear recoil from the far more common background events caused by natural radioactivity in the detector materials. The whole apparatus is surrounded by a tank of ultra-pure water, several meters deep, which provides additional shielding against the remaining radiation that penetrates even the deep rock. The detector is, in effect, a machine for achieving the deepest possible quiet, a technological monastery designed to hear the faintest possible whisper. LUX Zeppelin has been running for several years now, and it has not detected a WIMP. Neither has its Italian counterpart, Xenon T, which uses a similar design, a ton-scale liquid xenon detector buried beneath the Gran Sasso Mountain in the Apennines, and which has also been operating with extraordinary sensitivity. The absence of a signal is not failure, it is information. Each year that passes without a detection tells physicists something important, that WIMPs, if they exist, interact with ordinary matter more rarely than a given threshold. The experiments are drawing a shrinking box around the possible properties of WIMPs. A box that grows smaller with each passing year of data. The regions of mass and interaction strength that were once plausible candidates are being ruled out, one by one, with increasing precision. Some physicists find this silence troubling. The mass and interaction strength ranges that were theoretically most elegant, the ranges suggested by the WIMP miracle, are now largely excluded by the data. WIMPs may still exist, but if they do, they must be either heavier or more weakly interacting than the most natural theoretical expectations suggested. The parameter space is narrowing. Meanwhile, the search for axions takes a completely different form. The ADMX experiment, the Axion Dark Matter E experiment, based at the University of Washington, does not look for nuclear recoils. It looks for light. The device at the heart of ADMX is called a microwave cavity, essentially a hollow metal cylinder, precisely machined, which acts as a resonant cavity for microwave radiation, the same kind of electromagnetic waves your microwave oven uses, though at far lower power levels. The cavity is placed inside a powerful superconducting magnet that produces a field tens of thousands of times stronger than the Earth's magnetic field. The idea is this: if axions exist and are streaming through the detector, as they should be if they are the dark matter, since the solar system is moving through a halo of them at all times, then in the presence of the strong magnetic field, some of them will spontaneously convert into photons. The photons produced have a specific microwave frequency determined by the axion's mass. If the resonant frequency of the cavity matches the frequency of those photons, the signal is amplified enormously, because the cavity allows photons of the right frequency to build up resonantly, just as a tuning fork amplifies sound at its natural frequency. The challenge is that the axion's mass is unknown, which means the frequency of the photons it would produce is also unknown. The search is conducted by slowly tuning the resonant frequency of the cavity, adjusting its dimensions or the strength of the magnetic field, and listening at each frequency for any excess signal above the background noise. It is like scanning a radio dial slowly across an enormous range of frequencies, listening for a very faint station. The signals expected are extraordinarily faint. The power of the photons produced by axion conversion, even assuming the optimistic case that axions are the entire dark matter, would be something like 10 to the power of minus 23 watts, a number so small it is essentially meaningless in everyday terms. Detecting it requires amplifiers cooled to within a fraction of a degree of absolute zero, where thermal noise in the electronics is reduced to the bare quantum minimum. And yet the experiment works, and it is improving. Each year, advances in quantum sensing technology, amplifiers that approach the fundamental limit set by quantum mechanics, push the sensitivity further. ADMX has already explored and excluded a range of axion masses. The search continues. What the continued silence of all these experiments means, taken together, is not that dark matter does not exist. The gravitational evidence for its existence is overwhelming and independent of any particle physics assumption. What the silence means is that dark matter is shy, that whatever it is, it interacts with ordinary matter so rarely that our increasingly sensitive instruments have not yet caught it in the act. The universe is keeping its composition secret, and we are building ever more patient and ever more precise machines in the hope of overhearing a whisper. Science would be a much simpler enterprise if the evidence always pointed in one direction. Dark matter, as a concept, has accumulated an enormous weight of support. Rotation curves, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe. The case for its existence is, in the minds of most physicists, essentially settled. And yet there are places where the standard picture gets complicated, observations that do not quite fit, galaxies that behave in ways the models struggle to explain, and a persistent minority of scientists who argue with genuine rigor, that the answer to the dark matter problem might not be a new kind of particle at all, but a revision to our understanding of gravity itself. Begin with the galaxies that seem to have almost no dark matter. In 2016, astronomers using the Dragonfly telescope, an array of telephoto lenses working together, specifically designed to detect faint diffuse light, identified a galaxy known as Dragonfly 44. It was a large, faint, diffuse object in the Coma cluster, roughly the size of the Milky Way in physical extent, but containing only about 1% as many stars. When astronomers measured the velocities of the galaxy's stars, using the same spectrographic techniques Vera Rubin had employed, they found that the stars were moving much faster than the visible mass could account for. Dragonfly 44 appeared to be almost entirely dark matter, with a ratio of dark to visible mass even more extreme than typical galaxies. This was striking, but not contradictory. Dark matter models could accommodate a galaxy that was unusually rich in dark matter. What proved more difficult were the counterexamples that followed. In 2018, a team led by Pieter van Dokkum at Yale University identified a galaxy called NGC 52 DF2, another large diffuse galaxy, and measured its stellar velocities. This time, the result was the opposite of Dragonfly 44. Slowly enough that the visible mass of the galaxy could account for all the gravity needed to explain their motion, there appeared to be almost no dark matter at all. A second galaxy, NGC 152 DF4, showed a similar pattern. And since then, a handful of other galaxies have been found with apparent dark matter deficits, raising a question that the standard model has to work to answer. If dark matter forms halos around all galaxies as a natural consequence of how structure forms in the universe, why do some galaxies seem to have been stripped of it or never to have acquired it in the first place? One proposed explanation involves interactions with nearby massive galaxies. A large galaxy passing close to a smaller one can, through tidal forces, the same kind of forces that cause ocean tides on Earth, where gravity pulls more strongly on the near side of an object than the far side, strip material from the smaller galaxy, including its dark matter halo. If NGC 1052 DF2 formed in a region close to a much more massive galaxy and experienced such a tidal stripping event, it might have lost most of its dark matter while retaining its stars. The geometry and distances involved are consistent with this explanation, though it remains a subject of active debate. These anomalous galaxies do not disprove dark matter, but they complicate the picture, and complications are where the interesting science lives. The more fundamental challenge to the dark matter paradigm comes from a different direction entirely. The proposal that gravity itself might behave differently under certain conditions, and that this different behavior might explain galaxy rotation curves without requiring any new kind of particle. This idea was proposed in 1983 by the Israeli physicist Mordechai Milgram, and it goes by the name Modified Newtonian Dynamics, usually shortened to MOND. Milgram noticed that the flat rotation curves of galaxies seem to be related not to the total mass of the galaxy, but to the acceleration that its gravity produced. Specifically, the departure from Newtonian predictions seemed to kick in when the gravitational acceleration fell below a certain very small value, a threshold acceleration of about 1.2 times 10 to the minus 10 meters per second squared, which is extraordinarily weak. To put that in perspective, the gravitational acceleration at Earth's surface is about 9.8 meters per second squared. The MOND threshold is about 80 billion times weaker than that. Below this threshold, Milgram proposed, gravity does not weaken with distance in the usual Newtonian way. Instead, it weakens more slowly enough that the orbital speed of stars remains roughly constant even at large distances from the galactic center. In the outer regions of spiral galaxies, where the gravitational acceleration from the galaxy's visible mass falls below the MOND threshold, The modified law applies, and the flat rotation curve naturally follows. The remarkable thing about MUND is how well it works for individual galaxies. Given only the distribution of visible mass in a galaxy, MUND predicts the rotation curve with striking accuracy, often better than dark matter models, which have more free parameters to adjust. The relationship between the visible mass distribution and the rotation curve, predicted by MUND, has been confirmed across a wide range of galaxy types and sizes. But MUND struggles when applied to larger scales. It does not naturally explain the gravitational lensing in galaxy clusters. The amount of lensing observed in clusters like the Coma cluster requires significantly more mass than the visible matter provides, even with MUND's modified gravity. It also does not naturally reproduce the peaks and troughs of the cosmic microwave background, which fit the dark matter model so cleanly. Extensions of MUND to a full relativistic theory needed to handle lensing and cosmology have been proposed, but they tend to become complex and lose the elegant simplicity that made MUND attractive in the first place. And then there is the bullet cluster, the spatial separation of the gravitational mass from the visible gas, which so cleanly supported the dark matter interpretation, is difficult to explain in MUND. Modified gravity acts on the visible matter. It does not produce a mass distribution that can be spatially separated from that matter. The most recent significant development came in 2025 from a study led by Alain Blanchard at the University of Toulouse using data from the European Space Agency's Gaia satellite. Gaia is an extraordinary instrument, a space telescope that has measured the positions and motions of nearly 2 billion stars in the Milky Way with a precision that was previously unimaginable, mapping the three-dimensional structure and kinematics of our galaxy in unprecedented detail. Using Gaia's data, Blanchard's team measured the rotation curve of the Milky Way at very large distances from the galactic center. Distances so large that the measurements had previously been extremely difficult to make accurately. What they found was that the rotation curve does, in fact, begin to decline at very large distances. The speed of stars and gas decreases at the outermost measurable reaches of the galaxy. This is precisely what dark matter models predict. A dark matter halo is not infinite. It has an outer boundary, a region where the density falls off sufficiently that the gravitational pull it provides diminishes and orbital speeds begin to drop. The specific distance at which the decline begins and the rate at which it proceeds match the predictions of dark matter models. For MUND, this decline is more difficult to accommodate. In MUND, as long as the acceleration is below the threshold, the rotation curve should remain flat. A declining rotation curve at large radii is not what MUND naturally predicts. The Gaia result is not the final word. Science rarely works that way, but it represents a significant new piece of evidence. The Milky Way's own rotation curve, measured with the precision of a satellite that has spent years mapping nearly 2 billion stars, appears to favor dark matter over modified gravity. The dissenters will continue their work, and they should. The history of science is full of cases where the minority was right, but the weight of evidence in 2025 tilts heavily toward the particle, toward something real and physical, drifting through the galaxy, holding everything together, waiting to be found. There is a way of thinking about dark matter that has nothing to do with experiments or equations. It is quieter than that. It is the thought that arrives in the dark when you have stopped trying to understand and simply let the idea rest against you. Most of what holds the universe together is something we have never touched, never seen, and cannot yet name. That sentence deserves to sit for a moment before anything follows it. We are made of ordinary matter, the 5%, the atoms in your body, the air in your lungs, the light that reaches your eyes, the ground that holds your weight. All of it belongs to that small fraction of what exists. The rest, the vast, patient majority, is elsewhere. It is here, too, passing through everything, but it does not interact with what we are made of in any way we can ordinarily feel. Vera Rubin said it plainly, and it is worth returning to her words. In a spiral galaxy, she said, the ratio of dark to visible matter is about 10 to 1. And then she added something that has stayed in the minds of everyone who heard it, that this ratio was probably a fair estimate for the ratio of our ignorance to our knowledge. We are out of kindergarten, she said, but only in about 3rd grade. She said this without bitterness and without false modesty. It was simply an accurate accounting. She had spent her career measuring something she could not see, and she was at peace with the scale of what remained unknown. There is a kind of freedom in that, the freedom of a scientist who has learned to love the question as much as the answer, and who has come to understand that the questions worth asking tend to be the ones that do not resolve quickly. Rubin died in December 2016, and she did not live to see the direct detection of dark matter. Neither has anyone else. The question she spent her life illuminating is still open. The flat rotation curves she measured are still among the most compelling evidence we have. And the universe, for its part, has not yet chosen to make things easier. Think for a moment about what it means that dark matter does not rotate with the visible disk of a spiral galaxy. The stars and gas of the Milky Way orbit the galactic center in a great flat wheel, following roughly circular paths in a common plane. But the dark matter halo is spherical. It does not flatten into a disk because dark matter particles do not collide with each other and cannot shed energy through radiation the way ordinary gas can. They cannot cool down and settle into a common plane. They remain in their original, roughly spherical distribution, each particle following its own orbit through three-dimensional space, crossing and recrossing the galactic plane in trajectories that span the full volume of the halo. This means that our solar system, as it travels around the Milky Way, is constantly moving through a kind of dark matter wind, a gentle, invisible flow of particles streaming past us in all directions. Not a wind in the sense of pressure or force, because dark matter does not push against us. More like a river we cannot feel, a current we are immersed in without knowing it. Estimates suggest that in every cubic centimeter of space near the Sun, a volume about the size of a sugar cube, there are roughly 6 dark matter particles, if WIMPs are the answer. They are moving at velocities of around 220 kilometers per second relative to us, which is the orbital speed of the solar system around the galactic center. Trillions of them pass through your body every second. Trillions pass through the walls, through the ground, through the entire Earth, without leaving any mark we can yet read. The Earth itself, as it orbits the Sun, moves through this dark matter wind at changing angles over the course of the year, which means the flux of dark matter through a detector on Earth's surface varies slightly between summer and winter, by about a few %. Some experiments have looked for this annual modulation as a signature of dark matter, and one experiment, the Gamma detector in Italy, has reported seeing exactly such a modulation for more than 2 decades. The result is controversial. Other experiments with different detector materials have not confirmed it, and the source of the Gamma signal remains disputed. But the search for that seasonal variation is a beautiful example of how patient science can be, looking for a few % change in a very rare signal, over years of data, to find the heartbeat of something invisible. The scale of what we are dealing with is worth holding gently in the mind. The dark matter halo of the Milky Way extends roughly 600,000 light-years from the galactic center, far beyond the visible disk of stars, which reaches only about 50,000 light-years out. The halo is not empty. It is filled with this invisible mass, diffuse and vast, like an atmosphere that extends not a few 100 kilometers above a planet's surface, but hundreds of thousands of light-years in every direction. And the Milky Way is not unusual. Every spiral galaxy we have observed has such a halo. Every galaxy cluster is embedded in dark matter at a ratio of roughly 5 to 1. The cosmic web itself, the vast filamentary structure of the universe on the largest scales, is primarily a structure of dark matter, with ordinary matter tracing its outlines the way frost traces the edges of a window pane. When you look up at the night sky and see the stars, you are seeing perhaps 5% of what is there. The rest is invisible to you, but it is not absent. It is present in the most fundamental way possible. It is the reason the stars are where they are. It is the scaffolding on which everything visible was built. There is something deeply restful about this, if you let it be. The universe is mostly dark and mostly unknown, and it holds us anyway. The galaxies have been circling within their invisible halos for billions of years, unaware, as far as we can tell, of the mystery they inhabit. The stars shine, and the dark matter holds them, and neither one requires the other to be understood in order for the arrangement to persist. We are at an extraordinary moment in the history of science, a moment when the gap between what we know and what we can measure is closing, slowly, experiment by experiment. The underground detectors are listening, the microwave cavities are tuning, the satellites are mapping stellar motions with ever finer precision. The question of what dark matter is made of may be answered in our lifetimes, or it may not. The universe has not given any indication of being in a hurry. Kapteyn noticed something was missing in 1922. Zwicky named it in 1933. Rubin measured its effects across 60 galaxies in the 1970s. The bullet cluster showed us where it sat, spatially separated from the visible world, in 2006. Gaia began to trace its boundary in our own galaxy in 2025. Each step has taken decades. Each step has revealed more of the shape of the unknown. And the unknown, it turns out, is enormous, patient, ancient, present in every corner of the observable universe and in the space between your hands as you lie here in the dark. The dark matter is here now, passing through you. It has been here since before the sun was born. It will be here long after every star in the Milky Way has faded. It holds the galaxy together, the way sleep holds the mind, not through force exactly, but through a kind of deep structural presence, invisible and necessary, without which everything would simply drift apart. The question of what it is remains open, and open questions, when they are large enough, have a quality of peace to them. They remind you that the universe is not finished being itself, that there is still something vast and unresolved out there, waiting in the dark, patient as gravity. The night is full of it. Drift now, if you are ready. The question will still be there in the morning, a little closer to its answer, and the dark matter will still be passing through everything, quiet and immense, holding it all together. Keep well.